discussions. Okay, so the first talk will be given by Satya Majumdar. He's going to give us a blackboard talk or green board talk. Large deviations for the height in 1D KPZ growth models at late times.
Okay, so thank you, Chris, and thanks to the organizers for the invitation. It's a pleasure to be here. And so what I'm going to talk about is a recent work that was done in collaboration with Pierre Ledusal and Gregory Scher, and it's on the archive. So this is about the large deviations. I'll explain to you what I mean by that. For the height in one-dimensional KPZ growth models. KPZ stands for Kardar-Parisi-Zhang. Most of you know about this. And so at late times, we're asking what is the probability of very large height fluctuations? That's the main question. Now, KPZ problem, I mean, most of you are aware of, so let me just take you a quick summary. So essentially, there are various discrete space-time growth models were studied in the early 80s, mostly in 1+1 dimensions, but also in higher dimensions. So these are, like Eden model, ballistic deposition model, directed polymer model in 1+1 dimensions, and many other models. And all these models, essentially, you have some interface which is growing with time. So h of xt denotes the interface height at space x at time t. So there is a overall growth, and around the, the mean growth, which is linear in t, there is a fluctuation, and these fluctuations become larger and larger with time. Okay? And so a vast class of models were known to belong to the so-called KPZ universality class. That means the long wavelength and late time behavior of such models were described by this hydrodynamic limit by this continuum stochastic growth model, where you have del H del T, there's a diffusive term, there's a nonlinear term, and there's a noise term. And this was the famous KPZ model. And so in the 80s, people were interested in typical height fluctuations. That means height is growing, you ask at a given point, say at the origin, you look at the width of these height fluctuations and you ask how does it grow with time. And the width was typically growing like t to the 1/3 at late times in an infinite system. Of course, for finite system, it will be saturated, but let's not talk about finite system for the moment. And this 1/3 was a typical hallmark of the KPZ exponent. And those days, people used to say something belonged to KPZ university class. If this exponent happens to be the same for all these models, you would say it belongs to the KPZ university. And not just this exponent, but other exponents as well. But let's say this exponent for the moment. So this was the first phase of KPZ growth in 80s. And then there was a kind of, sort of another revolution which happened in the second phase, which is 2001, 2000 onwards. So there, it was realized that not just the second moment of the height distribution, but even the full probability distribution of the height happens to be universal in all these different models. So you calculate, for example, some of these models were solvable exactly, and you could calculate the full height distribution, and you would expect a scaling like this. So this will be 1/, this is for normalization, and then you have this typical height fluctuation scales like to the 1/3. So there should be a scaling function for the probability distribution. And this scaling function was computed for these growth models, and it was shown to belong to be what is called the Tracy-Widom distribution now. So Tracy-Widom distribution was first, it came in random matrix theory as the distribution of the largest eigenvalue of a Gaussian random matrix. But it so happened now that this distribution has appeared in many, many different areas, completely far from random matrix theory. And so, it's a big thing now that people find Tracy-Widom in all kinds of models, I mean, even in quantum dots and things like that. And so this is a distribution which is non-Gaussian tail. So for large x negative, it has x cubed, and for large x positive, it has x to the power 3/2. And so this was the second phase, and people had worked on various different models, and they found that all of them are described in the scaling limit by this KPZ, by this Tracy-Widom distribution. And then there was a third kind of revolution, 2011 onwards, where actually for the continuum KPZ equation, which was the tough part actually, and for this equation, it was people were able to solve it exactly, at least formally. And once again, you find that even in the continuum KPZ equation, the height distribution is, typical height distribution is given by Tracy-Widom distribution. And so here is this typical height fluctuation. So height typically fluctuates, this is PDF. Height typically fluctuates at order t to the 1/3. And so what we are asking in this work is how can we describe not typical, because Tracy-Widom will appear this white curve here. It describes typical fluctuations. But when the fluctuations are much larger, if you are asking for configurations where the height is much larger than t to the 1/3, Tracy-Widom doesn't describe that. Okay. So how can we describe these atypically large fluctuations at the tails of this probability distribution? So that's the question. So I want to look for height of order t, and the reason we are interested in the large deviation functions, I'll come in a minute, But let me tell you the main results that we find. So what we looked at is a particular set of initial conditions, which is called the Droplet initial condition. It turns out that in the Tracy-Williams distribution, there are four many classes. There is a parameter beta. So in this context, here it means it depends on the initial condition. If you start from a flat initial condition, you get what is called the F1 Tracy-Williams distribution. If you start from a droplet initial condition, that means you start growth from a seed site and grow it sort of in a curved geometry, then you call what is called the Tracy-Williams GUE distribution. So what we looked at is a droplet geometry. And so this is the typical distribution of height Tracy-Williams distribution that was well known before. We looked at the two large fluctuations. When the height is of order t, but on the negative side, that means I'm describing this tail here, it turns out it goes like exponential minus t square into some large deviation function of h over t. Whereas on the right side, it's asymmetric, it's actually t, and there's a physical reason for that. And there's another large deviation function, which is phi plus of h over t. And so these are called the rate functions or large deviation functions. And we could actually compute these two functions explicitly for two different models. So the first one is called the single step growth model. I'll describe in a minute. And the second is for the continuum KPZ equation itself. So single step growth model is variously known. It is called the directed polymer model. It's also a version of the anisotropic directed percolation model that Rajesh and Deepak looked at. It's also a version of the totally asymmetric simple exclusion process. So here is the model. So you start from a simple exclusion process. At t equal to 0, you fill up on the left half of the axis with you fill up with particles, and right side is totally empty. And so for each particle, you can put a vertical line like that on the dual lattice. So height at point x at time t is on. Is just the maximum. So it's a lattice model at discrete space-time model. So it's a maximum of the two neighbors at the previous time plus a noise which is distributed from an exponential distribution. Okay? So that's the model essentially. And so for this model, average height will go like 2t. And so if you center the height and define this centered height variable, then you can actually compute the large deviation function explicitly. I'm not going to tell you how we compute this, but these are explicit functional form for this large deviation function. And you cannot see from the back, for the KPZ equation itself, these functions are much simpler. It's actually z cube over 12, and it's 4/3 z to the power 3 by 2 on the other side. Okay? So basically you have, for all these models, these functions do depend on the, models, but what is universal is a small z behavior of these functions. When the z goes to 0, that means you are looking at height which is of order much less than t. So then they have to match the inner Tracy-Williams region, and therefore they actually become universal. So the question is, okay, you can calculate this, fine. These are non-trivial computations. But then, why are we interested in this? And this brings me to the last part of the talk, which is the reason we are interested in this is that if you look at this, if you plot this guy, this height distribution on a scale on the x-axis as h over t as opposed to h, okay? So then you see this typical width, which is t to the power 1/3, it reduces to a point, right? So this becomes a point, and you have this, large deviations on the probabilistical is a very small probability, so left and right. And it turns out that these correspond to two different phases. Okay, so this is called the strong coupling phase, and I'll tell you in a minute what that means. And this is weak coupling phase, and there is a phase transition exactly at that critical point. So here is this picture of my phase diagram. So if you look at the cumulative height distribution, it has these two behaviors, t square and t on both sides. So if you take the log of that, then this has the interpretation that this is the free energy of a strong coupling phase, and I'll tell you in a minute what is strong coupling. And so if you plot it as a function of z, so for z equal to 0, it goes to 0 as power of cube, and that's why it's called the third order phase transition. because the third derivative is discontinuous, and then it stays 0 beyond that. So this is called the weak coupling phase. So what is strong coupling and what is weak coupling phase? So just to tell you very qualitatively, so what you see, you can ask why is it t square qualitatively? So t square is the reason because you are asking for what is the probability. So height has a typical height here. You're asking for a probability of a configuration where the height is very small. Now, if the height has to be very small here, all the noise at different space-time, they have to be all very small in order to realize that configuration. So therefore, probability that these noises are independent noise variables. So basically, it will be e to the power the number of noise variables, and the area of this cone is of order x times t, which is t square, and that's the reason you have e to the power minus t square. And strong coupling, because all these noise variables have to act collectively in order to realize this height configuration. So that's why it's called a strong coupling configuration. Whereas on this side, if you want height at the origin to be very, very large, okay? So for that configuration, in order to realize that configuration, all you have to do is the height locally there, you just keep adding at the same point. Okay, you don't care about the neighbors, you just keep adding at the same point. And that's why, and because it's independent noise, so the probability of that configuration will be e to the power minus, t times whatever. So that's why it goes like t, okay? And here you see that, this phase, the weak coupling phase, there's no coupling between the different noises in order to realize this configuration. And so it's a weak coupling in the sense that it's one degree of freedom that dominates over the others. And so that's a generic picture of this. And in fact, we had a theory for recent times, from many different models, that wherever you see, so one of the questions you can ask, why is this Tracy-Widom distribution so ubiquitous? Why do we see it in so many different places? And one of the sort of things that we push forward in recent times is that wherever you see Tracy-Widom distribution, usually there is a third-order phase transition, on both sides of it, and they are captured only in the large deviation functions. For that, you have to compute the large deviation functions and check that this large deviation functions vanishes as a power of 3 as you approach the critical point. So the picture is that you have a strong coupling phase here, you have a weak coupling phase here, and Tracy-Widom is just a crossover function connecting the free energy of the two phases, okay? And so KPZ equation, the bottom line is that KPZ equation also has a third-order phase transition, which is not so visible, but it's hidden, and it sort of, you see it only when you compute the large deviation functions. Okay, so that's all. So. Yes, gauge theory, random matrix models, exactly. So all of them. Absolutely. Exactly. There n plays the role of time here.
N is large but finite.
Exactly. For finite but large, so when you take the n going to infinity limit, it becomes a real third order phase transition. Right. For finite but large n, you have this strong coupling, weak coupling phase, and they are connected by this crossover function. And that finite size crossover function is the Tracy-Widom function.
Why is t and t square?
Yes.
Why is phi 1 not?
Well, that's a non-trivial computation.
5 plus and 5 minus. That's just 5 plus and 5 minus not same.
No. They are not expected to be same. No, because there is an asymmetry here essentially, because there are two different phases. You don't expect free energies of two different phases in statistical mechanics to be same. So
another question is typically I always see Tracy-Widom as an extreme value distribution.
Yeah, no, but that's what I'm trying to say. Actually, it's not correct to think of Tracy-Widom as a extreme value distribution. It happens to be extreme value distribution in random matrix theory, but actually it's more associated to a third order phase transition. Okay. So it happens in many other models where it has nothing to do with extreme value theory.
In fact, it's extreme value with very high dependence.
It's not really,
So like for this height distribution, typical and atypical, it's near the origin, right? Along the...
Near the origin? No, I'm looking at the origin, at the Droplet geometry, I'm looking at the origin of the height, yes.
But if I look at one of the corners...
Yes. So all that happens is that the v, the velocity, will depend on x, wherever you are looking at. Okay.
But always you have the same Tracy-Widom, and also the large division is same.
Yeah.
It's independent.
No, large division functions will depend on x, of course.
Okay.
I just, that there will be x is a parameter. Okay. But it's always of this form, e to the power minus t. If you are looking at, for example, p of h of xt instead of h of 0t,
yeah.
So there will be a parameter x here, if you like. So I'm looking at x equal to 0, but any other parameter basically it will be. But they will always all go like z cube when you take this z going to 0 limit.
And this traceoidom is it true like if for large x?
Of course, yeah.
Is it
Traceoidom, yeah.
everything traceoidom?
Everywhere is traceoidom. Yes.
To some other such theory?
That's a good question. I don't know. Because usually, these kind of things, I mean, it's hard to see that because, Gumbel and all these things are for IID variables. And IID variables, they have to conspire, collectively in order to produce this, this strong coupling phase on the left, which is hard to see in that picture. I mean, in independent particle picture, I cannot see anything going like e to the power minus n squared.
Principle supposed to be valid for weakly correlated functions as well, even though.
Yes, that's true. Absolutely, yeah. So you need a strong, I mean, at least for this class of physics, I mean, you need strongly correlated variables.